Hello, Coach Travis coming at you with another calculus video. So this is a video about summation notation, about the interesting properties of summation notation. So anyway, so here's the problem. They tell us that the sum from 1 to 5 of 2 SI is equal to 28, and then they want us to use that information to find this guy right here. So we're gonna use a couple properties of summation or sigma notation to do this, and like the first one we're gonna use is this fact right here, that if you have a constant inside of your sigma notation, you can factor that constant out. So here the alpha is inside of the sigma, but here the alpha is outside of the sigma. And what I want to do is briefly talk about why this makes sense. So I don't want this to be some mysterious formula. So let's kind of look at an example. So suppose there's only like 3 terms here. Suppose there's just S1 and then an S2 and then an S3. This is just an example. Okay, but not so fast. Not so fast. We got those alphas that need to go there too. So let me get those alphas in there. So that there should be an alpha there, and there should be an alpha there, and there should be an alpha there, because everyone in this sum, every one of the SIs is getting multiplied by alpha. So an example, if A was 1 and B was 3, then this would turn into this. And now just think about, what do you know about addition? If I have alpha times something plus alpha times something plus alpha times something, if you just think about what you know about addition, you know that, oh, you could factor an alpha out of this. So it's not too hard to see that this is equal to, I could just have the S1 plus the S2 plus the S3, but then I factored that alpha out. So since multiplication distributes over addition, these two things are exactly the same thing. And now notice that's basically exactly what we have up here, because here's the summation, and that's what this is. This is a bunch of things being added together. So this is just the S things being added together, and then out in front of that is just the little alpha. So yeah, so the fact that these two things up here are the same makes sense, and the reason is simply this is basically just the distributive property, because over on this side the multiplication is on the outside, but then on this side, on the left-hand side, we've distributed the multiplication over the addition. Okay, so anyway, so back to this problem here. So how could I do this problem? So let me see here. Let me erase. All right, so now when I look at this problem, I see that there's another property of the sigma notation that I'm going to need to use, because there's a plus or minus right here. So there's a question of, what do you do when there's a plus or minus inside of your sigma notation? And so here's the general rule, is that if you have a plus or minus inside of your sigma notation, then you can split the sigma notation up across the plus or minus. So if it's the sum of the quantity Si plus or minus Ti, you can rewrite that as the sum of just the Si's and then plus or minus the sum of the Ti's. And let me give you an example of why that works. The reason that works essentially is because summation notation is just adding. Whenever this sigma is here, it just means add up a bunch of stuff. And so adding is something that's easy. So I mean, the sigma notation might be kind of scary the first time you see it, but really it just means add. And adding is something that's easy. Adding is something that we understand really well. And so all of the nice things that we know about adding, we can apply when we have summation notation. So anyway, let me show you what I mean with an example. So for example, this, like we said, this was just a bunch of SI's and TI's being added together. So for example, it might look like S1 plus T1, and then plus S2 plus T2, and then plus, oh, actually, you know what? Well, I'll go back and change it. Just to be a little bit more interesting, why don't we make these minus signs? So let me change those to minus signs. All right, so we'll go minus, minus, and here will be S3 minus T3. Okay, so that's essentially what this thing could turn into. Is it if I is 1 and B is 3, then this thing turns into exactly this, because it's, you put a 1 in for I, and then you put a 2 in for I, then you put a 3 in for I, and then you add them all together. And the reason I put a minus here is, again, is because in this formula you could have a plus or a minus. So what I'm about to do would work equally well whether you have a plus or a minus in between there. But okay, so now let's see what we got here. Since everything here is just being added or subtracted, so I bet you could convince yourself that I could just get all the I could get all the S's together. So I could rewrite this as S1 plus S2 plus S3. I could just get all the S's out in front, and then I could have a minus T1 minus T2 and minus T3. And then if I wanted to be a little bit fancy, I could put parentheses around the S's, the S1, S2, S3, and then I could factor a negative out of the T's, and then I'd have T1 plus T2 plus T3, because I factored the negative out, so I could write those all as plus. And now let's look at what we have on the right-hand side here. This is when you add up all the S's, and that's what I have right here. And then this is the sum of all the T's, and that's what we have right here. And I guess since I used a minus when I did the sum, this one will be a minus over here, which is exactly what we found right there. So the fact that these two things are equal should not be a real mystery. It's just the fact that you can rearrange terms when you add and subtract. All right, so now you say, great, Travis, thanks for all that abstract nonsense, but how do we actually use that to do the problem? And the answer is, well, let's see. Okay, so let's write down what we have to do. We have to figure out what the sum from I is equal to 1 to 5 of 3 times Si minus 1. We got to figure out what that is. Okay, well, thanks to what we just did, we now know that this summation can essentially distribute over that subtraction. So I can rewrite this as the sum from I is equal to 1 to 5 of 3 times Si minus the summation from I is equal to 1 to 5 of 1. Because again, that's just if you kind of imagine the summation, the sigma distributing over the subtraction, then that's what you get. And then we can say, oh, well, hey, this 3, that is a constant. And we said you could factor constants out. So you have 3, this will become 3 times the sum from I is equal to 1 to 5. Oh boy, that was a bad 5. To 5 of SI. And then minus the sum from I is equal to 1 to 5 of 1. Okay, so now we have to figure out what the heck is this guy and what the heck is this guy. And okay, well let's do the hard one first. So the problem did tell me that the sum over here, the problem did tell me that the sum from I is equal to 1 to 5 of 2 times SI is equal to 28. And so like we said before, we could factor this 2 out. So you can always factor the 2 out of your summation. So 2 times the sum from I is equal to 1 to 5 of SI is equal to 28. So again, it's still equal to 28 because these two things on the left are exactly the same because all we did was factor the 2 out. Oh, okay, but now we can divide both sides by 2. So, all right, so that's going to say that the sum from I is equal to 1 to 5 of SI is equal to 14. If we divide both sides of this by 2, the 2 goes away on the left, and the 28 turns into a 14. So awesome. So we know that this right here is a 14. And then, okay, so now all we have to do is figure out what this is. But think of, I guess there's another property of summation notation that I could talk about here, but I'm actually not even going to bother. I'm gonna just think. Let's think about what does this mean. Well, it means so when it might be confusing here when you look at this because you say, wait, there's no I. What do we do? Well, the idea is this is just a constant function. So I think about what do I get when I put I equals 1 into this function? Well, the correct answer is you just get 1 because this function is always returning 1. Okay, and now you take I is equal to 2 and put 2 into this function. And what do you get when you put 2 into this function? And don't say 2 because you get 1. This is the function that's always equal to 1. So no matter what I put in, I'm always going to get 1 out. So when I is 1, I get 1. When I is 2, I get 1. Now next I'm going to do I is equal to 3. But when I is 3, I still get 1. Then I'm going to do I is 4, I still get 1. And then I do I is 5, and I still get 1. And I stop there because you stop when you get I is equal to 5. So the moral is this just turns out to be 5. Because it's just going to be 1 plus 1, wait, 5, yeah. 1 plus 1 plus 1 plus 1 plus 1. All right, so that means we got our final answer here. Our final answer is going to be 3 times 14 plus, or it's actually, oops, I almost made a mistake, it's minus. 3 times 14 minus 5. And let's see, what's 3 times 14? 42? 42 minus 5, and so that's, what's 42 minus 5? 37? So, all right, I'm calling this one 37. And then we're all done with that. So the idea there was what we did first was we used the fact that a summation notation can distribute over an addition or subtraction. So we broke this into two simpler summations. And then we used the fact that constant multiples inside of a summation can get factored out to make it even simpler. And then we also used that if you have a summation of a constant, then really what you just get is you get the constant multiplied by the length of the index. So if the index is starting at 1 and ending at 5, well, there's 5 numbers there. So you're going to get 1 times 5. And if this was a 2, then we would have gotten 10, because we would have gotten 2 plus 2 plus 2, 5 times. And then so you put all those together, and then you got your